I am making experiments with 3 crystals in one oscillator. At 10 MHz, each crystal is equivalent with an inductor in series with a resistor. That resistor is about 80 ohms. And RA, that is the input impedance of the amplifier. And there will be 3 amplifiers. For some preliminary tests, I have replaced these amplifiers with 10 ohm resistors. And first I can connect the network analyzer and measure the transmission from the input to one of these resistors. So I connect the network analyzer here, which means that the load is going to be a little bit lower than 10 ohms here. And according to the datasheet, I should expect the Q to be 1250, but when I put 10 ohms in series, it should go down to 1.11 million. Here is what I see close to the carrier. And it says Q is 1.2 million. So it's a little bit better than the specification told me. When I look at a somewhat larger frequency span, I see the parallel resonance here. And at the bottom, it's not the transmission, it's the noise floor. When I span a wider frequency range and look at the impedance, I have disconnected the 10 ohm resistor, of course. Then I see it is only a 1.8 kilo ohms, and I want it higher. The 1.8 kilo ohms is the parallel capacitance of the crystal. I can tune it out in 2 ways. I can put an inductor to ground, or I could put an inductor across the crystal. With an inductor across the crystal, the advantage is that I get a symmetric frequency response. So maybe that can affect the phase noise close to the carrier. When I look with a narrow span, I can measure the Q again, and it has dropped from 1.2 to 1.16 million. So that's not really what I want. This is the coil I was using, which had inadequate Q. The wire is very thin and there are many turns. Inside the porcelain tube there is a ferrite core that doesn't go all the way through the copper winding, because from the other end there is a copper slug that can be moved to reduce the inductance slightly. It can go about 2 millimeters into the winding. I have replaced this by a tunable core with much thicker copper and not so many turns, in series with a toroid from material 4C65, so the total inductance is the same, but Q is higher now. Now there is no parallel resonance anymore. The transmission through the filter is symmetric. Q is now 1.195, so it's a very small loss in Q. The output impedance from the filter is now higher, about 7 kilo ohms, and I'm spanning 100 kilohertz now. I have disconnected the cable to the network analyzer and adjusted the electric delay to get the highest possible impedance, around 150 kilo ohms. This way I know that the instrument is correctly calibrated to that end point of the cable. When I look at the Schmidt diagram, I can read that the impedance is minus 150 kilo ohms. Obviously that's incorrect, it's just the noise I see. But calibration is very accurate now. So I connect the cable to the filter output. When I look at the impedance well below the resonances, I see 2.6 pF. That's the stray capacitances I have. When I look at the impedance magnitude, I see 6 kilo ohms. That's the 2.6 pf. And near the center, there is the impedance from the filter making a contribution. I can balance those 2.6 pf by using an inductor to ground. That will be the DC path for the emitter current, and it's good to have something with very low losses there. This is the first stage of my selective amplifier that will become an oscillator when I apply feedback through it. Within the blue region there are 3 amplifiers and 3 crystals. When I continue with the next stage, the outputs will be in parallel, but right now I have separate outputs because I want to investigate this amplifier now. I have 3 amplifiers, so I have tried 3 different transistors to see whether one or the other is better. These inductors balance the parallel capacitance of the crystal, as you have seen with my measurements. This inductor balances the stray capacitances to ground from the coil here and wires and from the crystals. This is to prevent microwave or UHF oscillations. 47 ohms and a thin wire, 10 turns on it, and 8.2 pf to ground. That has stopped the oscillation I have seen so far. This capacitor is a small ceramic multilayer which gives a very low inductance and good decoupling for the base. And I have selected 1 kilo ohm because previous experiments indicate that it is not necessary to go much lower than this. Here is the equivalent schematic diagram for the unit we just saw the detailed schematics for. I want to show this because there could be some misunderstanding in how this works. Each crystal is an inductor in series with 80 ohms on the fixed frequency 10.0000. And then I connect the amplifier in series, that's about 17 ohms. Now when I connect parallel this inductor with some series resistance with other inductors and series resistances, I get a lower, about 3 times lower inductance for all these, and about 3 times lower series resistance as well. So I get the same Q, but there is a lower impedance. I have to put the 3 times bigger tuning capacitor to tune this 3 times smaller inductance to resonance at 10 MHz. And then I have a coupling capacitor to set a suitable signal level into the system. And if the crystals are a little bit different, it doesn't matter, because they are just parallel inductors, so they will have a common resonance at 10 MHz. When I measured Q previously, the bandwidth level was set to 2.91 dB. I didn't know how to change that, but now I found out. And now the values I measure agree perfectly with the specification from the manufacturer. Previously, I found values being too good. This one is labeled 672. Here, 672 should be 1.225 million. I checked that with the network analyzer, but I have lowered the impedance by putting 5.1 ohms to ground on each side of the crystal. So with the network analyzer in parallel, that means that I have set it in a 4.5 ohm system. So effectively I have put 9 ohms in series with the losses of the crystal. The Q I see varies a little bit due to noise. 1149, 1146, 1148. You can see the arrows here move a little bit from time to time. That's because the temperature is unstable and the temperature drift is significant when the crystal is at room temperature. But I think 1150 could be a reasonable average. I measured 1150 kilo, and I can compute with the values from the table here. 81.6 ohms in series with 9 ohms times 1.225 million. That gives me 1103 kilo, and I find 1150. That's close enough for me to be satisfied. Then with 18 ohms, which is the average impedance into my amplifiers, I should expect Q about 1020 K. What I see is not quite as good. It is 928,000 for this particular amplifier, that they don't differ much. When I compare the three filter amplifiers, I find some differences. The BFQ69 is best when it comes to the ratio between output impedance at the center frequency and the wideband, 16.9, while the BFR 134 is about half of that. The input impedances don't differ much. It's highest for the BFQ69 and lowest for the BFR 91A. And they are all about the same. The reactive part mean there is some inductance, but not very much. I could tune it out, but I don't think that matters. The Q is the same for all three, and I think the Q is actually a property of all three crystals and the balancing inductors for the parallel capacitance. The signal level is different, but not much. It differs by 1.4 dB at most. And then I have looked at the noise floor, and it differs, but not very much. But together this gives a signal-to-noise ratio, which is best for the BFQ69. And I don't know if any of this is really significant. What is significant is the low Q. I don't know the reason for this, and I will look a little bit if I can find an explanation. I have placed an inductor on the same kind of core that I have used in the box, and this is parallel to the crystal, and I have selected a number of turns to get a good balancing of the parallel capacitance on the crystal. The Q I see is high, 1.2 million, and this is with a 9 ohm series resistance from that setup. And when I span a wider frequency range, I see a nice symmetric curve. Now I understand what mistake I have made. When measuring the losses of the inductor by looking at the series resonance in a 10 ohm system like this, the voltage across the coil or the impedance level it is sitting across is very low. It's 80 ohms from here to here through the crystal. So if the losses in the coil is significantly larger than that, there's no problem. But in this configuration, the inductors are sitting across the crystals, means like this. And now the crystals have a high impedance because this capacitor and the combined inductance of all three form a parallel resonance circuit with a high impedance point here. So then losses become very important. So I have to find another solution. I have modified like this a signal in antiphase. Typically one would just have a trimmer capacitor from here to here, but that small capacitors, I don't have any of them, and it's inconvenient to have something inside the box. This capacitor I can adjust from the outside, and it gives the same phenomenon. A voltage divider capacitive and then a small capacitor to here. Now I see a Q of 1.06 million. That's pretty close to what I expected. And when I span a larger frequency range, this is 10 kHz, I see a nicely symmetric frequency response. Now, when I no longer lead the inductors that were sitting here, I will move the components upwards because I made the box a little too small. I need some more things to place here. Amplifiers and limiters. Here is the impedance at 2 MHz sweep width for the signal feeding the amplifier. I have disconnected the amplifier. The impedance level is much higher now, about 100 kilo ohms. That's because the losses from the ferrite cores are no longer present. And the lower frequency is because there are bigger stray capacitances. Here is what the unit looks like now. I had forgotten the emitter resistor and its decoupling, and I had to add a small capacitor here to ground to stop VHF oscillations. This is now 0.75 pf to 1.5 in series. And I found that with 11 dBm of input here, I got 100 microwatt power dissipation in the crystal, which is the maximum rating. Then I could observe 60 millivolts peak to peak here across the input impedance of this amplifier. And that was with load here of 25 ohms, because that's the design target I have. The only significant change that happened when I changed the method of getting rid of the parallel capacitance of the crystals is the Q. It has gone up from 928 to about 1070. But other things are not much affected. The crystal ratio, of course, has also increased because the losses far from the resonance has become reduced. I got rid of the losses of that parallel inductor. And this will be good for the noise far from resonance, I hope. Input impedances have not changed much. I did not keep track of which transformer was combined with which transistor, but the changes from here to here are very small. I measured before the noise only with a 50 ohm load on the port where I was measuring the noise. And that gave me some signal to noise ratios. What I see now does not differ much, essentially the same. I have also measured with a 25 ohm load on the output. Then the excess noise is very small, so I have computed the actual noise power that is added by the amplifier, and it gives these values for the signal to noise ratio. So it is best for the BFR 134 and then the BFQ 69, and the BFR 91A is about 1 decibel less good. And whether this is a valid measurement, I'm not really sure. This is the noise at wide separations from the carrier, so it is not really very interesting. Here is the input impedance. On the resonance, 46.7 ohms, and off resonance, 49.4 ohms. I can do some simple mathematics. Off resonance I see 49.45 ohms, and on the resonance I see 46. Two parallel resistors, I can compute the unknown one, and I arrive at 856 ohms. With 11 dBm input across the 46.75 ohms at resonance, I develop 767 millivolts across the input. So the 50 ohm load, this one, gets 11.8 milliwatts, while the crystals absorb 690 microwatts. Now, part of that is heating the input of the amplifiers, which are 19 ohms, so 81% of that heats the crystals. That becomes 188 microwatts per crystal. That is a factor 1.9 above specification. Not too horrible, but maybe I should reduce the input power a little further on. I will look at performance, what happens, and so forth. And since this is how I calibrated it, it will show now infinite impedance. And now, with a 50 ohm dummy load, it of course shows 50 ohms, because this is how I calibrated it. And now I connected a short, and then of course I see a short on the Schmidt chart. And now I can measure the output impedance of one of the amplifiers while presenting 25 ohms to the test port. What I see looks pretty odd. I have two resonances, it looks like. 2 points where the impedance has minima. And I placed markers 1 and 2. 1 on the weak resonance and 2 on the strong resonance, as one would think from this graph. And here is transmission through the unit to one of the outputs, and the strong resonance, number 2, is some false thing, and here is the main transmission. So this was surprising. And here is I have been looking before for the Q and for the transmission through the box. And it is 1.1 million. It looks very good. And this loss, I take it as a relative number to use for the future. Minus 19.6. I have connected all three outputs in parallel by use of some T-connectors, and I will measure with my 25 ohm network analyzer this T-connector with a dummy load on it. In transmission I see minus 12 dB. That is 7 decibels stronger now. But the Q is degraded. It's only 910,000. Now when I span 2 kHz bandwidth, I no longer see that extra resonance. And when I look at the output impedance that is seen by the 25 ohm network analyzer, this is what I see. And I have a capacitive 423 pf in total. I can cancel that by adding an inductor. And I can do that by changing the electrical delay. So I can see that the ratio between on the peak of the filter and off is fairly large. I have added some lengths of cable to shift the phases a little between the different amplifiers. That makes a difference. The Q is now 1.017 million. And that is good enough, I think. And the signal level has dropped just a little. It is now minus 13.5. The impedance doesn't look any good anymore, because these fairly long cables give a significant impedance change. So the amplifiers are not loaded by 25 ohms anymore. I think this problem can be corrected by adding some reactance in series with the crystal. That is something I will look at later, because first I want to find out if there is any difference between the transistors. I have checked the power measurement, and actually I had forgotten to check the tuning of this capacitor, so it was not tuned exactly on the frequency of my Wenzel oscillator, as I thought. So the power needed is not 11 dBm, it is 8.9 dBm. Needed to get 60 millivolts peak to peak in this point. So the error I made was 2.1 decibel. So I have to divide these 188 microwatts by 2.1 dB, which is 1.62 times. And that gives me 116 microwatts per crystal. So that's about the maximum that I should operate at. Here I'm using the interferometer with 30 decibels of carrier suppression to look at the phase noise of the BFR 134. Particularly bothersome is all these interference pulses. I don't know what that is, if it is really this amplifier or if there is something else. And here is the amplitude noise, and we can see phase noise is much stronger than the amplitude noise. The reason could be that I have been a bit lazy. I have connected the signal to this point without disconnecting the crystal, but I have put the resistor just 1 ohm from here to ground to minimize the effect of different loading from the crystal. And the input impedance this way is about 19 ohms. I have disconnected the crystal now, and I have set Linrad to record raw data, which you can see from the blinking S here. So if there still are these problems, I can look at the input to see the nature of the problem, perhaps. I may have found the problem. This BNC connector, when I try it, I can sense that there is no contact with the screen these first 5 millimeters, and then I can sense that the inner contactor gives a substantial contact pressure, but the contact pressure is almost zero for the screen. So I will bend the fingers outwards a bit on this, and a couple of other ones of the same make that I have. I am now looking at the BFR 91A. I have seen that this fairly strong event was an amplitude pulse in the channel 1 signal. And since there is nothing in channel 2 at the same time, there is no contribution or almost no contribution to the correlation result. So it doesn't affect this yellow trace much. I can see that the noise at large separations is higher. I read minus 164.4, and for the BFR 134 I had minus 167.2. So that's a 3 dB difference. Now the instabilities in channel 1 have become too disturbing. You can see it is high above, and there is a lot of interference here. And one can see here that the green trace lifts now and then. The phase noise of the BFR 91A is very similar to the phase noise of the BFR 134 in the close range, up to about 100 Hz. The wide floor is a little bit higher, by 3 decibels. The amplitude noise is slightly lower in the close range, but above 100 Hz or so, it's the same as the phase noise, because that is the white noise of the amplifier, which is independent of the carrier phase. Here is the phase noise of the BFQ69. This has been running overnight, so statistics is very good. And I can see that at 1 Hz I have minus 111. That is minus 141, a single dB better than the other amplifiers. And when I look at the PN2060C, I see a different value. It looks like minus 103 or so here, even though the marker is a bit below. So the performance given by that unit is not the same as I see in Linrad. Maybe that's because the level of the device under test is far too low for that unit. But the wide floor here comes out exactly the same as in Linrad. Minus 137.4 or so. Minus 137.2. Well, here is amplitude noise and phase noise in the same diagram. Correlation between them is 0, below 10 Hz. And here, where the zero frequency is of the direct conversion, there is some correlation. But then at higher offsets, there is no correlation. So they come from different sources. And phase noise is much stronger than amplitude noise. I have changed the source impedance from 1 ohm to 80 ohms. That's what is the source impedance very close to the carrier. It has not made any difference at 1 Hz, where I expected something to happen, but it has reduced the noise floor at large distances from the carrier. I see now minus 139.2, means minus 169.2. That's an improvement with 2 decibels. Not much, but maybe with a much higher feed impedance, as would be at these large separations, the noise floor is going to be a little bit lower. The amplitude noise at 1 Hz offset has increased from minus 147 to minus 143.5 now. And it is clear now that there is correlation between amplitude and phase noise. So they have a common origin. And the separation between amplitude noise and phase noise is not so big anymore. And we can see that at large separations, the amplitude noise is stronger than the phase noise out here. Small differences, but means something, I don't know what. I have been running with an output voltage twice as large as the design target. But now I have reduced the power by 6 decibels, and that had a dramatic effect. I can see at 1 Hertz the noise floor is now minus 120, means minus 150 dBc per Hertz. At higher offsets I cannot measure anymore because it's below what I can see. And the PN 2060, it deviates more because now the signal level is 28 or 27 dB below the normal signal level for accurate measurements. So these levels I see here are far too high. And the transistor is the BFQ69. The source impedance is still 82 ohms. Interesting is that the amplitude noise now is stronger than the phase noise, but they are probably uncorrelated. But measurement is not very accurate because this is below where I can do measurements accurately. Here is the BFQ69. I have changed the power from 12 volts to 16 volts. I see no difference at 1 Hertz. It is still minus 150 dBc per Hertz. At 10 kilohertz I now see 132.1. It was 132.5 with the lower supply voltage. The amplitude noise at 1 Hertz is now minus 146, and it was previously minus 145.5. Well, that's maybe not statistically sure. The BFR 91A is a little more noisy than the BFQ 69, about 1 decibel for phase noise. And the amplitude noise, on the other hand, it seems to be significantly better. It's equal to the phase noise at 1 Hertz, and also at wide separations. This is the BFR 134. It shows minus 120, but if I make a straight line here, it's more like maybe 119.5. Anyway, it doesn't differ significantly from the other transistors. At 10 kilohertz, it says minus 132.3. The amplitude noise is at 118, means minus 148. That's also a little bit better than the BFQ69, but differences are really small. When I compare AM and phase noise, I see that the amplitude noise is a little bit stronger than the phase noise here around 100 Hertz. I don't think anything is significant of what I have detected about the transistors now. I want to measure the time delay or phase shift through the amplifiers. To that end, I have disconnected the crystal at this point, and I feed the signal in here and take it out here, of course. I will use the tiny PFA and connect one cable here and then move the cable between these 3 different outputs. This means that 2 of the amplifiers will see 50 ohms, while the one I'm measuring will see 25 ohms. Now, when changing the output loading, the input impedance here will change. Not very much, but it will change from, I don't remember exactly, maybe 19 to about 25 ohms. Now, with this big resistor and then a small resistor here. A change from having this one 82 plus 19 to 82 plus 25 will not change the signal level in this point significantly. So what I can see when looking in one chain, it doesn't matter if I load or do not load here. So that is convenient for comparing the phase shift. The signal level is low, so I had to add an amplifier to bring the signal level up so the performance of the tiny PFA becomes normal. In this situation, stability above 10 seconds is not impressive. The phase is drifting. I will wait until tomorrow to see if it has become more stable. Well, this is stable enough to measure differences. Here I measured all three: BFR 91A, BFQ, and BFR 134, and back to the 98A and the same order. And I magnify this, and then I can read what the different delays are. This one is close to 0, and here is 6.6 times 10 to minus 10 seconds. At 16 volts, the power is 2.21 watts. I step the supply from 16 to 14 volts, like that. And then I see a step in the phase immediately. But, as you can see, the phase is now starting to drift away. And that is probably an effect of the temperature, and I will wait now for some time. The power has dropped to 1.67 watts. That's a difference of 0.54 watts. After 5 minutes about, the temperature effect has shifted the phase by as much as the capacitance variation, which is immediate. And that is for a change in temperature of about 1 degree. After half an hour, we have almost reached an asymptote at 2.5 times 10 to minus 11. The temperature has stabilized at 38.2 degrees. I have returned to 16 volts, and the immediate step is of the same size as before, from here to here. And then comes the temperature effect. And the slope here initially is similar to the slope here. And the temperature is back as 40.1. And the transistor tested this time was the BFQ 69. I have made the same test on all three amplifiers. And I find that the BFR 134 has a peculiar behavior. When I change back from 14 to 16 volts, it's the same drop as the same step here, but after that there is this peculiar behavior, while the other two transistors behave as one would expect. This curve, if I look close to it, it's like this, and on the other side, when I move the other direction, it looks like that. And that is near, this looks perfectly okay. But I don't understand what that could be. Here is the summary of all my findings about the transistor amplifiers. The upper three lines were with the inductors, the loss inductors that degraded Q. So what this matters is the lower three lines. I have marked with green where something is significantly better than the other ones, and yellow if it is nearly as good. So most greens are in the BFQ69. This ratio between the impedances on the center frequency and at the flat noise floor, what I call crystal ratio, is largest for the BFQ69 and significantly larger than for the other ones. And then the signal to noise ratio is best for the BFQ69, but almost as good for the BFR 134, and that's the wide noise floor. But the difference is just a single decibel. And that was with 50 ohms load. With 25 ohms load, the BFR 134 was a little bit better, but the difference is still very small. But the BFR 91A is more than a decibel below. Phase noise at 1 Hz, it doesn't differ. And also at 1 kilohertz, the differences are so small, so this can be because of the inaccuracy in my cancelling of the carrier by 30 decibels. Well, this is significant, but those don't differ significantly. Amplitude noise is significantly better for the BFR 91A. But amplitude noise is not very important, I think. Delay, I don't think that matters. The sensitivity to a voltage change is much better for the BFR 134 as compared to the other two. But this parameter, I'm not so sure it's so important. I see that the thermal effect is bigger than the direct step, which is caused by the varying capacitance over silicon junction. I have reconnected the crystals and placed BFQ69 in all 3 amplifiers. And now I have measured the phase shift through the 3. Starting at 0 here, something times 10 to minus 13. And the third amplifier here is 3 times 10 to minus 10. This is the same order of phase shift as I had in the amplifiers. So the problem is perhaps not the crystals. To verify that, I have selected 3 very different crystals, one above 10 megahertz and the one about 5 hertz below, and one in between. I have placed them here and they are connected with 27 ohms to ground, and then I have connected this unit, which is a hybrid splitter with 3 ports. So they are loaded by another 50 ohms, and they don't see each other because the hybrid isolates. And when I measure Q, I see 1.2 million. They do have a common resonance. They work as I theoretically thought. So the problem is the amplifiers. I used this hybrid to combine the 3 amplifier outputs while loading them by 25 ohms each and having them isolated from each other. And then the Q became perfectly okay. So I connected the 3 signals with a wire, so all 3 were connected. Made no difference at all. So I realized I cannot load the sum of the 3 amplifiers by 25 ohms. I have to load with 25 ohms divided by 3. Here is the impedance with all 3 amplifiers in parallel. It looks very good, I think. The capacitance is 191 pF on one side and 170 on the other. So about 180 pF has to be compensated with an inductor. I can simulate that by setting an electrical delay. And then I find that on resonance I have 80 ohms, but off resonance the impedance is about 1 kilo ohm. So this looks very good. With this arrangement I can test how Q and signal level varies when I put different numbers of 50 ohm dummy loads on these T connectors. With just a single 50 ohm load, that's the network analyzer itself, the Q is 758,000 and the level is minus 7.74 dB. I have looked at up to 11 50 ohm loads. Here are the results. I have measured Q and level in dB, and this is the impedance that I load the box with. The power totally delivered is the level, and it's distributed to this number of loads. So this is the total power delivered, and this is computed as the 1 over Q squared, which is the loss, compared to this which I consider having no loss, and I can lose up to 3.5 decibel in the close range phase noise. And the power that should give the signal to noise ratio far from the center. So I can lose up to 6 decibels by having a very low impedance. It seems reasonable to go for something like 10 ohms. So if I set that to 0 and then compare with the power, which gives signal to noise ratio in the wide range, and 1 over Q squared, which gives the close range signal to noise ratio, I set this as 0, I can see that by going to 12.5 ohm, I lose 0.3 dB in the close range, but I gain 0.8 dB in the wide range. Well, maybe not. If I go in the other direction, I can gain 0.2 decibels while losing only 0.4 decibels in the wide range. Well, this could be better. Going further in this direction, going from 0.18 to 0.32, well, tenths of a dB, losing 2 or 3 tenths. Maybe, but further down, the loss starts to become too large, I think. Anyway, this is the compromise between close range and wide range noise floor. Should be pretty obvious looking at this. But exact what to go for, I couldn't say until I really have an oscillator to see what performance I'm getting from it. I have added a second amplifier stage like this. When running with the nominal power input, I get 11 milliwatts output. That is 1.5 volts peak to peak across 25 ohms. And that's the load I have to present here to get the 10 ohm input impedance into this amplifier, which is what the previous amplifier wanted. This inductor removes the capacitive component from the previous amplifier's output impedance. I have run it with and without this inductor, which removes the capacitive component of the output impedance that I see here. There are some differences, not very large. I'm sending 9 dBm of power from the Wenzel oscillator into the unit. And here is what I see, and I can compare it with a fresh measurement of the Wenzel oscillator. It's like this, and there are subtle differences, particularly here, where the noise is going down by maybe 4 decibels or so. But at 10 Hertz, the difference is small, and very close to the carrier means long time stability, 100 seconds. I have a loss of performance. There is some instability which is clearly seen. And the white noise is very much higher than I had hoped for. So this indicates that this isn't really a good idea after all. But at 100 Hertz, there is a significant difference. When I look at the amplitude noise, I can see that the unit I have just made degrades performance. Here is what I see now, and here is what I saw when measuring on the Wenzel oscillator. And the amplitude noise is below what I can measure with this time. It was only 50 minutes, but you can see 140 here, and it is far below, and there are blue lines in, which means that the real value is far below what I see here. So the unit is noisy, more than expected. Here is the frequency response. The total span is 20 Hertz, so the separation 2 Hertz gives 0.5 dB, and 5 Hertz, that's here, gives 2.6 decibels. I make a table out of this. For some reason, the final stage no longer presents 10 ohms to the preceding one. It gives more than 20 ohms. But that doesn't matter for the moment, because now I'm interested in the noise, which is too high. I have saved screen dumps of all the measurements, and I edit now with Irfan View, and I can put the mouse on some position on the screen like that and read the position. It says Y is 294 here. So I can read out easily, accurately also, the positions of various things on the screen. In this region I can avoid the spurs and see where the curve would go if there had been no spurs. Like this, for example, that is 2101 in pixels. Here is what I have found. Plotted in the low section here is the frequency response of the filter. So 3 decibels is here. And if I look, the red is the Wenzel, the blue dots is the Wenzel through my selective amplifier. And they have exactly the same values, this range. Below 0.2 Hertz there is some extra noise added by my selective amplifier. Some stability issue there. But when we have 3 decibels of attenuation, that's here, I can see that the curve is almost the same. The yellow dots is what I get when I subtract this filter response from the Wenzel. So I could have expected that I should see the curve go like that, but it doesn't. So it seems that at this point my selective amplifier starts to add phase noise. Or could it possibly so that my measurement system adds phase noise somehow? I don't know. I cannot explain what I see here. But I can see that my selective amplifier has a higher wide range noise floor than the Wenzel. And of course the noise floor from the Wenzel cannot pass through the filter, so It's just that my selective amplifier, if I would turn it to an oscillator, it would have not quite as good wide noise floor as the Wenzel oscillator. So this is something I do not want to see. I can say up to this point my results are not satisfactory at all. I discovered why the Q was not good at all. I had made a mistake. I had a tap here that I used, but that was incorrect. When I made the design to get 10 ohms, I had to put the output directly on the collector. Now the Q is much better. As you can see here, 1.14 million. So this is what I designed for, but I had forgotten when I moved that test into the box. Here is the output impedance, 564 ohms on the resonance and 7 or 8 kilo ohms off resonance, plus minus 300 Hertz, because there is 600 Hertz sweep width now. To get the desired Q, I have to load the output with 25 ohms. And by doing so, the connection to the sideband noise analyzer will be very close to 50 ohms. Like this, now I'm connecting the network analyzer to the output with a 50 ohm dummy in parallel. The output power is much lower now, because the mismatch is much larger. And there is one odd thing I can do. You look at the screen now, what happens? There is something with distortion. And that is because I have a magnet here and I move it like this. Not very close to that ferrite core. But this gives a significant change. And I don't know whether it affects phase modulation or whether that ferrite could be a source of phase modulation. It is a 65, material 65 core. It has rather high permeability as compared to the ones I used for the first amplifier stage. I thought that would be a good idea. Maybe it was a bad idea. When I look at the spectrum analyzer, I find there are oscillations at 1.7 gigahertz. And that could not be good. I realize I had drawn the diagram incorrectly. This is how it looks. And the problem with microwave oscillations was when I connected the output here. And that was of course wrong. I need this to isolate for microwave, to get a resistive impedance for microwaves for the collector. So when I put the output at the proper place here, the situation is different. The signal level is higher now, 600 millivolts, and when I take that magnet and move it close to the iron, nothing happens. Even if I put it right on the iron like that. So microwave oscillations were harmful. I connect the network analyzer and look at the output impedance, and it has become significantly higher. And Q has increased, but very little, from 1.14 to 1.158. And I think this is fairly reproducible because I'm running slowly at a narrow bandwidth. I press bandwidth once again. And it still says 1.15877, that's 8. The phase noise is significantly lower now in this region. The previous measurement of the same thing was like this. This is the Wenzel oscillator filtered by my selective amplifier. The previous, when the Q was not so good. And now it looks like this, and I cannot really say what the noise is in the region from 20 Hz to 100 Hz. So I have to disconnect the direct conversion receiver, because I think most of the spurs here are related to overtones of 10 MHz from the direct conversion receiver that leaks into the PN2060C. And I have to increase the signal level because it's too low by about 10 decibels. This was no good. This has been running half the time compared to the previous measurement, which I have here. I have scaled it to the same size. Look at the light gray here. It's the imaginary part with all the spurs and problems. Now the imaginary part is at the same level as the real part. It has increased. You can see here is 170, and it's also here. And in the previous measurements, the imaginary part was down here with spurs. Now it's up here. It's more than 10 decibels stronger in this region. So it seems that the amplifiers I have added are adding phase noise. They are on the other side of the hybrid in the two channels into the correlation system. So they don't give any correlated noise. They give uncorrelated noise from the two uncorrelated amplifiers. So this didn't answer the question I have. How is performance in this region? Unknown. And waiting for a factor of 2 more time will not ease the situation, because it would take 10 times more time if it even would work. Now, this is a little better. There are still great many spurs in this region. I think that is because of the PN2060 itself. And I'm not sure where the limits for the performance is. I saved the previous measurement like this, and you can see here at 100 Hz it's down at the flat noise floor, so phase noise has to be almost 3 decibels below. And if you look here, for example, looks like 3 or 4 decibels. I magnify and read the pixel positions, and this is difficult at 0.01 Hz. The uncertainty is large, but if I look at a wider range of points, I say, well, about here would be the correct position. Between 1 Hz and 10 Hz, I have a nice smooth curve with a good separation to the imaginary part. So these are reliable measurements. The most interesting part between 20 and 100 Hz is noisy, and I don't know to what extent the spurs that I can see in the imaginary part affect the result. But I make a smooth curve here and measure what I think is reasonable. So, for example, at 70 Hz, I would say here, but uncertain by maybe plus minus 1 or 2 decibels. With proper loading of the second amplifier, the filter becomes narrower. It's the second curve here, and it's about 3 decibels below what I had before, above the corner frequency. But the noise I measure, I mark that with crosses. Up here it's better than before, but this is 10 seconds and a stability issue that I'm not worrying about at this point. Here the crosses come on the same line as I had before, but above 5 Hz I see an improvement, and it is significantly better by about 3 decibels at 30 Hz and 2 decibels at 10 Hz. And at this point here the crosses are 3 decibels above the flat background, which means that the phase noise is down here, and it fits to some. But I had expected far lower if I had to take into account that the filter attenuation out here is about 20 decibels. So 20 decibels below the Wenzel oscillator. It's down here, and this additional 3 decibels, it's down here. So slightly better, but there are still significant problems of unknown nature, means of, for me, unknown nature. What is particularly interesting is the fact that if I look at 1 Hz, for example, where the passband doesn't suppress anything, just a fraction of a dB, the noise that comes from the Wenzel oscillator, which is on this line, if there were phase noise generated by the amplifier or the crystals, then that noise should add and bring the curve down. But that doesn't happen. I see only the noise from the Wenzel oscillator and nothing added by the crystals and the amplifiers. But when I go a little bit further out, let's say here, when the Wenzel noise is suppressed down to this level, I see much higher noise. I have no explanation what is going on here. Here I'm using a pair of SDR-IP units to measure the phase noise. But that doesn't work well because the SDR-IP uses an 80 MHz oscillator, which is phase locked now to my 10 MHz references. And that is fine at 1 Hz offset, and I can confirm minus 120 decibels here, and with a good distance to the imaginary part, which is the red dots you can see here. But at 10 Hz, the imaginary part is at the same level as the real part. And if I look at 50 Hz, that's here, I have seen minus 166. But here I see minus 150. That is 16 decibels. That is a factor of 40, means I would have to measure 40 squared as long time. And it is now 21 hours. So this is absolutely meaningless. On the other hand, at 1 kHz, I can confirm the level minus 170. And maybe I could modify the PLL circuitry to get a curve more like, but I don't know how to do that. I have again connected my direct conversion receiver, and it's now running in parallel with the PN2060C. It has been running for 68 and a half hours, so it's a very long time. I can compare this with an old measurement that was with the incorrect load impedance, and that's this. In Linrad I can see minus 152 dBc per Hertz at 10 Hz offset, while the PN2060C gives me minus 150.9 at 9.93 Hz offset. So there is a small difference. I don't know whether it is significant. Anyway, when I look in the PM2060C, I see these things between 100 Hertz and 500 Hertz that I think are internal spurs of the PM2060. I don't think they had anything to do with the addition of the direct conversion. On the other hand, these spurs at, is it 18 Hertz about? No, it is 12 Hertz or so. And twice 24 and so forth. That's the audio frequency from the direct conversion receiver that somehow enters into the system and their harmonics. When I shift the vertical scale in the Linrad spectrum, I can see that from 10 Hertz to about 200 Hertz, what I have is noisy, despite the very long time. And it's also a problem in the PM2060C. From maybe 30 Hertz up to 300 Hertz. So my tools are not really good enough to study this region. I will save these things to have to compare with when I have converted the unit to an oscillator. I can blow up the screen of the 2060C to see the details between 10 Hertz and 1 kilohertz much better. And actually it seems I can read here information that is correct. I mean, the green trace is high enough above the imaginary part here, 10 decibels below. And above 100 Hertz there are many strong spurs, but even so the green trace seems to be a flat noise floor all the way down to 100 Hertz. Looks like about 1 decibel addition of the phase noise at 100 Hertz. Here is the amplitude noise, and it's strong enough above the imaginary part, so this is the amplitude noise I'm really measuring. And here is what it looks like when I show amplitude and phase noise at the same time. And I can see that at about 5 Hertz already, that's around here, the amplitude noise and the phase noise are correlated. Not very strongly, but they are correlated to some extent. So they have a common component, although it's not dominant. And then at the audio frequency, where things are not correct because there is a notch at 0, meaning that the level goes down very close to this spur. I cannot say much about what happens above 10 Hertz and below maybe 15. But then I can see that the amplitude noise is a significant thing at 100 Hertz, and this must be generated by my amplifier stages. It cannot pass through the filter. And already at 10 Hertz I see noise generated by my amplifiers. But it's amplitude noise. The amplifiers don't generate phase noise, or at least not much. I think what we see here is just a white noise from the amplifiers. I have added a third amplifier stage like this. When loaded by 100 ohms here, to test it I have made like this, connected 75 ohms and 50 ohms to ground, and then I measure with the phase noise test system, which presents 50 ohm here. Then I load by 100 ohms here. That means that the load in this point will become 25 ohms, And that's what the previous stage wants to give the good cue that I am aiming at. And this third stage, it's designed because here is what I will put a limiter. And that will have a push-pull signal of a suitable amplitude and a low impedance. So I will get the low noise amplitude limiter. And then I can make an oscillator. Here is what I see with the third amplifier also in line. I decided it is not possible that it will add significant amount of phase noise. So I made another experiment at the same time. I have reduced the supply voltage from 16 to 8 volts. That's 4 times less power, but this does not affect the gain through the amplifier chain because it's determined by negative feedback. It has been running for 13 hours, and I can compare it with the result I had before, here, when running 68 hours. And the big difference is the noise here. It has improved by about 2 decibels, and I can see an improvement also here at 50 Hertz. Small, but very clear. So that's interesting. Will be much better to study such things when the unit operates as an oscillator. It has not been running long enough to see any significant differences in the Linrad measurement with the direct conversion receiver. Statistics doesn't allow any conclusions. Here is a close view of my result now with all 3 amplifier stages, and here is the previous one. I have added an amplitude limiter to BFQ 69, fed from this low impedance source from the third stage, and it is limiting without saturating the transistors. And from this point I connect to the input, and I get the same signal level as I had when running with the Wenzel oscillator at the input. To do that, I had to increase the supply voltage slightly. I don't want to load here, so I take out the signal through a fairly large resistor, 330 ohms. And then I put 50 ohms to ground to have a 50 ohm source for the sideband noise analyzer. Means I attenuate by 23 decibels, so I'm looking at a very small signal. Here is what I see after 34 hours. I can compare it to what I had with the Wenzel oscillator. That's here. And the result is rather interesting and not exactly what I have expected. When I look at the result with Linrad, at 5 Hertz, for example, it is about 2 decibels better. But at 1 Hertz, here, it is degraded by about 2 decibels. And here, with the PN2060, it's hard to see. But there is an improvement here. Small. But here is a more significant improvement. But there are some peculiarities, interesting things. If I look at the amplitude noise, I have to click here. I see there is a significant amount of amplitude noise. And when I look at amplitude noise and phase noise at the same time, I see that there is a strong correlation. So amplitude noise and phase noise have a common origin, and they are strong at 5 Hz, where the noise actually was lower than with the Wenzel as the driving source. And when I look here, I see that the spectrum is not symmetric. The noise is on the high side of the carrier. It has to become asymmetric if the AM and phase modulation are correlated. So that is expected from the correlation. This is the output into 50 ohm. I have set the oscilloscope for 50 ohms. I have connected the Wenzel oscillator and removed feedback, and as it turns out the signal level is a little bit lower, so I have increased the supply voltage a little bit too much. But that doesn't explain why I have that noise source that affects both AM and phase noise. This is what I see with the Wenzel oscillator into the selective amplifier, and looking at the output from the limiter. The noise floor here is very high. I compare with what I had before I added this limiter, about 10 decibels lower. And you can see it also in Wienrad. Here is what I have now, and what I had before was 10 decibels down. We don't see it here. Then at close range, 1 Hertz. Now it is here, and before the same. So I'm adding wideband noise from the feedback output, but I have a degradation at 1 Hertz when running it as an oscillator. Then there is an additional problem. Starting here, it seems I have an interference in channel 1. I think this is the BNC connectors. I have to take apart and clean them, some more of them. This has come and gone a couple of times, and I don't know exactly where the problem is, but it is a connector problem. I have allowed the system to run for a couple of more hours. Now it's almost 5 hours. The extra noise in channel 1 has disappeared by itself, and now I can see that on all frequency offsets, what I see now is not as good as I had when not using the limiter. Here, the difference is very small at 1 Hertz offset, but it becomes larger and larger the larger the offset is. So this is now on the limiter, and this is the stage before the limiter. And there is a clear difference already at 10 Hertz. The problems with noise from the limiter could be caused by microwave oscillations. With this instrument I can look up to 1.8 gigahertz, but there could be problems at even higher microwave frequencies. To see if I have problems with microwave oscillations above 1.8 gigahertz, I have made this microwave probe. It's a 1N21 diode. Should be okay up to the X band, that's 10 gigahertz. And it's just a diode and a small capacitor, 1 PF, to connect it to various things. I have set this generator to 2 gigahertz, 0 dBm. And I use this voltmeter in the diode test mode, So I see here the forward voltage 0.168, and when I touch here I see this changes down to 1.113. So this is a way of seeing if there is microwave. I can change the level and then it even goes negative. And I can see it couple even at a small distance. I have used the microwave probe on the limiter and everywhere else in this selective amplifier, and there is no microwave oscillations here below 10 gigahertz, and the transistors are not faster than that. So that isn't the problem. I have attenuated the signal from the Wenzel oscillator by 50 decibels. That means that the limiter now works as a linear amplifier. And I can see there is a lot of noise. Is it 30 megahertz? The total span is 200 megahertz. Also at 100 megahertz there is a lot of signal. If I disconnect, this is what we see. So I save this. I have placed a 100 pf capacitor between the bases of the differential amplifier, that is the limiter. That has reduced the 10 megahertz signal by about 5 decibels, but this 30 megahertz about 15, and 100 megahertz by much more, of course. This will still be a limiter because this is with margin strong enough to bring it into saturation. I will see what it makes to the sideband noise. The 100 pf capacitor has reduced the noise from the limiter significantly. Here is what I had before, and now like this. So about 5 dB. And there is a difference even at 1 Hertz offset. It says 120.4 now, and here it says 119.4. And we can see that the track is a little bit higher. And also here at 10 Hertz. I realize now that wideband amplifiers in front of a wideband amplitude limiter is a bad idea. If I think in the time domain, noise with a bandwidth of, 150 megahertz adds up to a significant peak amplitude. And when that adds to the 10 megahertz signal, the point of zero crossing will move around and introduce phase noise. And that will affect phase noise even at a point here, which is far above the level of the noise as seen in the frequency domain, like this. So I will stop here with this experiment, remove those wideband amplifiers and put narrowband amplifiers there instead. That will be the next video. And by the way, the extra noise in channel 1 has suddenly come back at this point in time, 15 minutes ago or something, and you can see here also. Now it doesn't affect the phase noise result, but it slows down the convergency when I'm going to start a new measurement. And you can see it is going up